All right, so how's everybody doing out there? Well, hopefully that little extra video kind of helped clear it up for people if you were a little confused about when to use which normal curve for which inequality and when to kind of think about things and stuff like that. So at least it helps me, so hopefully it helps you guys as well. So today we want to move on to talking about testing a claim about a mean when sigma is unknown. So if you remember, this is going to be our t interval situation that we're talking about. And this is definitely going to be more realistic than what we did with the z interval just like before. So t interval, because again, it's very rare that you're going to know the population standard deviation without actually knowing the population mean. So again, section 9.5 is probably the more type of hypothesis testing that we're going to get used to. So it's good to get, make sure we know how to do these kind. So let's just dive in right away and do an example since we're already kind of familiar with the process and stuff like that. So in this case, we've got, since Halloween just occurred, I thought I'd have you guys test the following claim. So according to Mars, a typical bag of M&Ms contains 18 brown M&Ms. I claim that orange M&Ms is significantly different than brown M&Ms. So I sampled our class. So normally we would have been able to do this, but I couldn't share M&Ms with you guys because of Corona, and I'm not actually seeing you. But so I sampled our 24 students, found the sample mean of orange M&Ms to be 18.5 with a standard deviation of 2.4. Can I conclude that orange and brown M&Ms have about the same number of M&Ms? So let's find out. Who knows? So in this case, so again, I like to just jot stuff down, just because I can. So in this case, let's see, what are we starting off here? So we've got our n is 24, so our number of students. We found our sample mean to be 18.5. Whoops. We found our sample standard deviation, so this is in the population, so I'm using S, to be 2.4. And let's see. I think that's all we need. So, and there's no alpha given. So in this case, we can just assume that alpha is 0.05 in this case. So again, remember, doesn't matter what kind of hypothesis test we're going to do. We still have the same exact, 4-step process each time. So again, state the hypothesis first. So since this one is significantly different, that's the equals not equals situation. And so 18 is kind of our mean that we're testing against. So our H naught and our H1, so we've got mu is equal or not equal to 18. Our H naught is mu equals 18 in this case. So that's our hypothesis. So now what we want to do is we want to calculate the test statistic for this guy. So again, like this is going to be our two-tailed test. So notice I've already got the picture drawn for you. So what that means is that if we wanted to kind of work backwards to figure out what this is, so this is going to be, 0.025 on this side, 0.025 on that side is what we're looking at. And so if we wanted, we could actually figure out, well, what would be the t-score that would give us that? Because again, it's nice to have multiple ways other than just the p-value to find out whether we're going to be landing that range or not. So I like to do this. I mean, it's not necessary, but I think it's kind of fun. So like if I work backwards and do the inverse t function, so if I do second vars inverse t, then I can get, let's see, what do I want? 0.025. So I want to get the lower end, comma, my degrees of freedom, which are 23. So that's going to give me a z-score, or a t-score of negative 2.07 in this case. So that means the edge of this blue is going to be negative 2.07. And then that means the upper will be exactly the same because it's symmetric in this case. So let's actually calculate our test statistic to see where we fall in that region. So in this case, we get our 18.5 minus 18, all divided by, let's see, our 2.4 divided by the square root of 24 in this case. So let's throw this in the calculator real quick and see what we get. So 18.5 minus 18 divided by 2.4 divided by square root 24 gives us a t-score of, it looks like 1.02 in this case. So our t-score is 1.02. And so remember, like where u equals 18 would be t equals 0. So in this case, without even like doing any more calculations, I can kind of say, okay, well, my t-score is going to fall somewhere in this 1.02 range. So it's not going to be, I would need a t-score bigger than 2.07 or smaller than negative 2.07. So I can already tell just by looking at this that I'm in the fail to reject range. But it doesn't hurt to go and actually throw it in the calculator just to verify that, you know, we haven't messed something up or something like that. So, but my gut instinct, based on just the picture alone, tells me that this is going to be a fail to reject. So, and that's why it's nice to know more than just one way to do these. Like, it's nice to be able to look at the pictures, look at the t-scores, things like that, just to get an idea of where these guys should live and stuff. So let's actually calculate this to see what we get. So in this case, we're going to use our, which one is it? So, oops, in the wrong thing here. Oh, I guess I'm still using just normal CDF to calculate this. So yeah, so I'm still using normal CDF. So I'm not using anything different. The only thing I use different is the inverse T in this case. So let me go back because I forgot to write down what I was supposed to be doing. So in this case, so this is the two-tailed one. So I'm going to do normal CDF 18.5 comma 100,000 comma 18 comma 2.4 divided by square root of 24. And then again, remember, whatever answer I get to this, I want to multiply it by 2 because it's the two-tailed test. So let's throw this in the calculator. And in fact, if you wanted, you could probably do it this way. Well, we'll just do it normally. So normal CDF 18.5 comma 100,000 comma 18 comma 2.4 divided by square root of 24. So I get 0.153, multiply that by 2, so I end up getting like 31%, which is definitely, you know, supports kind of the picture that I drew. So in this case, we've got 0.31 or 31%. So in this case, 0.31 is definitely bigger than our alpha level of 0.05. So it looks like in this case, we're going to fail to reject H naught. There isn't sufficient evidence to support the claim that there's a significant difference between orange and brown M&Ms. So again, so notice I did this kind of two different ways. I did the p-value, which is our 0.31, but I also used the t-score and figured out where like my outside t-scores would be, where I would need to land in order to actually be in that blue area. So I kind of got a double confirmation that I actually did this right. So again, that's one of the reasons I like to do these more than one way, just so, like, 'cause you never know if you type it in the calculator wrong, and that's the only thing you're going off of. You're just gonna, keep firing straight ahead, thinking, oh, okay, I've got this right. But for me, I kind of knew based on my picture, it's like, oh, okay, well, this shouldn't work anyway. And so getting 31% is like, oh yeah, that definitely didn't work. This is nice. So again, kind of use these different ways as ways to either check yourself, or just do them in general. Just to kind of keep an eye on things. All right, so there's a couple more for you guys to practice. So we got practice 1, practice 2, practice 3. And then when you're done, come back. I'll have another video so we can talk about probabilities in this case. So good luck finishing up Sigma Unknowns, and I'll see you at the next video.